say.
Oh, but that is that yesterday's stream?
Yes, yesterday's stream
Oh,
including like all of the chit chat we had in the beginning. So
oh,
maybe we can at least cut off the beginning somehow.
yeah. Okay.
Say?
Oh, but that is that yesterday's stream? Jesus Christ. That was me going live with this today's stream.
Um, Michael, for the video, when I download it, do I download both the text file and the video, and then should it automatically play the text? Or is there like a certain video player you played it through?
So I've used VLC. Um, that's just been the easiest for me.
Yeah. Okay. I'm sorry. I I'll try it once more, but I might have you do it if it doesn't automatically load this time. Yeah, would you mind sharing your screen for the video portion? I'm sorry about that. I just realized that BLC needs admin permissions.
No worry. I understand. Um,
Hi,
that being said, I'm gonna just try sharing my screen.
Okay.
my name is Craig Brinkerhoff. I'm a postdoc at the Yale School of the Environment, and today I'm going to briefly introduce two examples of using SWOT data to improve hydrological understanding in river basins and river systems around the world. So,
Was that good?
Yeah,
Okay.
I think so.
Yeah, that was great.
And could you see any of like the floating bars or any? Was there like the gray boxes? Okay.
Not that I remember, no.
No, I don't think so.
Okay. It's unclear when Zoom puts the gray boxes over things and when it doesn't.
Yeah.
One of the many ministries in universe.
Both.
I might just go through the slideshow real quick too, if that's okay. Or unless you wanted to, Michael,
No.
instead. Um, so should I show kind of go through exactly what was gone through on day one with like the sixth Amen J workshop, fourth virtual workshop, about 525 registrants, day two. And then should I read out the code of conduct on this slide?
So I think Robert like just went through the bullet points,
Okay.
and I'll drop a link to the full code of conduct in the chat.
Okay. And just mention that we're the Aquatic Ecosystem Modeling Network Junior. Okay. Okay. then give a background on hacking Limnology series. This is just a highlight, but okay. So I don't need to like name everyone, but just this is our 2024 organizing team. Okay, great. And here are workshop leaders. Is this a time where I should introduce them, or probably not until the next slide when it gets to this? Okay. And if you're interested in staying connected, you can join our Slack here. Okay, great. You can access all the workshop materials and information on the GitHub page. And today we'll be focusing on remote sensing.
Oh.
Here were yesterday. So should I just delete this and just have the remote sensing here? Okay. Should I keep the ecological modeling for tomorrow or just have the remote sensing people? Okay.
I think
I
just
mean, if you want, you could say one sentence to both, that yesterday we had this easy map day and tomorrow we're going to have another day of workshops, but I think that's enough from
Okay. And then mention the brainstorming sessions after this workshop. Great. And then say that we'll have 3 breakout rooms for socializing, questions, and brainstorming. Okay. Yeah. And then just move into letting you screen share for Craig's talk, pretty much, right?
Yeah.
Okay. Thank you.
Yeah, of course.
And should I have it up on the screen, I guess, to start? Okay. Hi, Craig. Thanks for
Howdy.
joining. Let us know if you have any questions. And I'm sorry, you'll have to see a recording of yourself talking.
No worries. I'll put myself on mute.
And does my audio sound okay? Okay.
Thank you.
Should we start letting people in?
Sure.
Let's do it.
Hi, welcome everyone. We'll just get started in a couple minutes. Let me know if you can't hear me. All right, well, maybe I'll get started. Okay, great. Hi, everyone. My name is Merritt Harlan, and I'll be introducing today's session. Welcome to the Hacking Limnology 2024 First Joint Virtual Summit and Workshops. Today, this summit generally focuses on data-intensive aquatic research. This spans many different types of fields and methods that we've shown here below, and it's quite an inclusive community in terms of the scope and breadth of our research that we'll show. This is the 6th AIM&J workshop and our 4th virtual workshop, our 5th Data Science and Open Science Summit, and we have over 525 registrants. And welcome to day 2, everyone. Here's our code of conduct that Michael will link to in full. The main points I wanted to highlight are to use welcoming and inclusive language, to be respectful of different viewpoints and experiences, to gracefully accept constructive criticism, focus on what is best for the community, and show courtesy and respect towards other community members. Who are we? We're the Aquatic Ecosystem Modeling Network Junior, or AIM&J. And this is the Hacking Limnology series. AIM&J started as a grassroots network of early career aquatic ecosystem modelers and have organized several workshops, including 2 annual workshops in person in 2018 and 2019 that included about 207 global members. They're heavily connected to GLEON, or the Global Lake Ecological Observatory Network, and our first Hacking Limnology series was in 2021. Here's our 2024 organizing team, and if you're interested in being a part of it, feel free to reach out to any of us. And here are our 2024 workshop leaders. If you're interested in staying connected with this group or joining AIM&J, here's a QR code and link to our Slack channel. You can also find us on GitHub or send us an email at that link below. We also have a GitHub site for this Hacking Limnology series where you can find links to the different workshop days or the Data Science and Open Science Summit. And we also have other postings on jobs or information, as well as a great and extensive archive from all of our trainings from years past. So I encourage you to check out this link and site if you haven't already. Here's an overview of the week. Today, we're going to focus on remote sensing. So if you're interested in regional, continental, or global change, try using satellite data is our pitch for it. And today in particular, we're focused on the surface water and ocean topography satellite. Yesterday, there was talks on global lake modeling through ICIMIP, or sorry, yep. And today we'll focus on remote sensing. There's a pre-recorded introduction to the surface water ocean topography satellite that you can stream on your own, and that's up on the GitHub site. today we'll be live streaming a keynote talk by Craig Brinkerhoff, who's a postdoc at the Yale School of the Environment, titled Tracking the World's Rivers with the SWOT Satellite. Craig's done really fascinating research on SWOT and its link to the global carbon budget and many
So Merritt froze for me. So with that, I'll queue up Craig's keynote.
Hi, my name is Craig Brinkerhoff. I'm a postdoc at the Yale School of the Environment, and today I'm going to briefly introduce two examples of using SWOT data to improve hydrological understanding in river basins and river systems around the world. So, very briefly, right, we need to monitor global rivers if we're at all interested in trying to successfully understand and in turn manage our freshwater resources around the world. But this is deceptively difficult, right? Monitoring ability is limited because, quite simply, we can't put a sensor or a gauge or sample in every river on Earth, right? Even in an ideal scenario, you might have a river system with these 5 gauges spread at these handful of rivers in the network, but we're still missing monitoring in the vast majority of the system, right? And even at these places where we do have gauges, there's often significant temporal gaps or limited temporal representation in these monitoring networks, right? This can be due to kind of limited sampling, changing operations, or funding landscapes that kind of turn gauges, on and off. Here's an example: global stream gauge network, where the number of operating gauges has largely plateaued since the late 70s, and a lot of gauges have gone offline since 1980. The point here is where our observational network of rivers is really there's big gaps in it, both in space and time, right? And that holds us back from being able to monitor global rivers and watersheds and manage resources. And so one way to address this that scientists are increasingly using is satellites, right, to try to fill in these gaps. You're never going to replace in situ sampling or gauges because these are the gold standard, but satellites can certainly extend and expand existing monitoring networks, and in places where we have absolutely no ground information, they're invaluable in kind of improving our hydrological understanding of a system that previously we had no knowledge about. So SWOT seeks to directly address this observational gap issue in rivers and lakes, right? SWOT has a bunch of different goals, and it has an entire other half dedicated to oceanography, but to a river surface hydrologist, right, the SWOT satellite seeks to directly address this observational gap issue that plagues us in river science. So briefly, how does SWOT work in the context of rivers? So SWOT is measuring water surface extent and elevation for most rivers on Earth. And we can see 2 examples here of that water surface extent extracted from a river in Madagascar and France. When we talk about the resolution of SWOT measurements, we're looking at river measurements made made once every 3 to 21 day repeat cycles, meaning in Arctic rivers in kind of northern latitudes, you can get up to 3 measurements made approximately every 3 days, and obviously less frequently at lower latitude. There's also a very special 3-month window during calibration of the satellite where we have a completely novel, invaluable data set of 1-day repeat sampling over the same rivers that all fall under the same longitudinal band. And all of that data from 2023 is now available. Finally, spatial resolution. SWOT is measuring rivers at least 50 meters wide. And so that's every river that you see in this map. The benefit of this type of spatial and temporal sampling from satellite should help fill in some of these observational gaps. We'll also say that preliminary work suggests that in the future we'll probably be able to extend this down to even smaller rivers, right? This is a photo from a press release when SWAT kind of first started producing data, observing 20-meter wide canals, and it's one of the kind of lower level data products. And ongoing work is showing that we can see rivers that are 10, 15 meters wide. So promising. So with all that context, the goal of this talk is to just very, very briefly introduce 2 examples of using SWAT data to improve hydrological understanding in river systems. And I'm going to introduce first a very mature kind of community level project and goal that's been working for the better part of 2 decades. And then briefly at the end, introduce a much kind of less mature, younger project. And hopefully through all of this, I can provide some context and motivation of how folks are using SWAT river data. Again, provide some context and motivation for your research moving forward, what SWAT might fit in. So, remotely sensing river discharge. So many of us already know this, but discharge is the volumetric flux or flow rate through a river channel, the volumetric flux of that water. And because water accumulates as you move through rivers downstream through river systems, Q ends up being this sort of master variable that integrates all upstream watershed processes, right? So it's kind of this master variable that's really important across a variety of freshwater domains: water resources management, water quality management, flood forecasting and control, ecological studies and modeling, and looking at hydrological responses to climate change. It's really one of the fundamental properties that we need to understand in surface hydrology. And so going back to the early aughts, people have been trying to think of ways to get Q from satellite data to try to fill in some of these spatial and temporal observational gaps. What we're going to do now is introduce the way that idea has kind of accumulated over those past almost 20 years to being able to infer river flows from SWAT data. There's other ways to remotely sense discharge from satellite data products, but we're going to here just focus on the how we're producing the official NASA and CNES river discharge data product. And this is being done through a huge community level effort with 6 different algorithms producing. So how does it work, right? SWAT measures inundation extent and water surface elevation, meaning we're measuring river width, water surface slope, and water surface heights. And you see here, right, a time series of river widths at a river cross section that are being extracted from SWAT data. Those primary data then get fed into equations for flow through an open channel, right? These are geomorphic and hydraulic expressions for river discharge. These are the 5 sets of equations behind these 6 algorithms. Those of you who may be more familiar with these will know that obviously we cannot directly measure all of these terms using SWAT. Specifically, we cannot directly measure channel roughness or channel bathymetry or shape. And so the real novelty behind these techniques and approaches is using statistical techniques to try to solve these equations, which are very poor or strongly under-constrained or ill-posed, right? There's a lot of unknowns relative to knowns. And so briefly, the way we do it is we come up with this idea of priors, first estimate approximations of what roughness and bathymetry might be, given domain knowledge and auxiliary data. And then, depending on the algorithm, use a variety of statistical techniques to constrain uncertainty in the system of equations and infer river discharge from this ill-posed problem. I won't go into it, but very, very briefly, generally, this is done either using Bayesian inference directly or data assimilation, where these SWAT data are assimilated into hydraulic models. So the community spent about a decade refining these through proof of concept studies, right? Benchmarking on simulations of what SWAT data might look like, doing regional studies. This is the Mackenzie River watershed, the largest river basin in Canada. More benchmarking studies, building out an operational kind of pipeline to run these 6 algorithms in the cloud and produce the river discharge data products that are going to be hosted on PODAC. And eventually, we were able to run the whole pipeline on some of the first rounds of high-quality SWAT data. And so I'm going to show a few hydrographs here showing when we're producing pretty good estimates of river flow and, like, conversely, when we're not doing as well. So here are 4 examples. So these purple lines are going to be the ensemble of your 6 SWOT discharge algorithms. So the median across the 6 algorithms, so that we're robust to different assumptions and idiosyncrasies in all of these. And then black is the institute gauge. And importantly, remember that the purple line has no ground information in it whatsoever. It's solely obtained from SWOT measurements. And you can see it works pretty well. Right? Sometimes the algorithms blow up a little bit. Sometimes we miss these peak flows. But in general, it's working reasonably well for relying on no ground data whatsoever. In these cases, it's not working quite as well, right? Sometimes the algorithms oscillate. Sometimes they're all over the place. Sometimes you get the dynamics, but the whole hydrograph is kind of squished due to kind of ultimately its prior bias. These are, I guess, the 2 end members of this first run of river discharge from SWOT, right? And the rivers fall somewhere in between here. If we zoom out and look at all 188 rivers in this validation test that we did, we get this. And so this plots a lot. It's CDFs of performance metrics across these 188 rivers. I want to just draw your attention to the red line, okay, which is validation of the ensemble predicted river discharge estimates. And we're using KGE, again, that's the performance metric. To the right is better. And the main takeaway here is that just over half of these 188 rivers are outperforming a uniform prediction of the mean, meaning we're improving hydrological understanding, and we would be improving hydrological understanding in an ungauged system with SWOT discharge. And so that's a really promising first result, and we expect these to continue to improve as SWOT data quality improves, as we refine our algorithms, as we get more information and to define these kind of priors and roughness and bathymetry. So this is a good, quite promising first cut result. And I also want to again stress that this plot right here is the culmination of, again, nearly 20 years of work by a large community of folks. So that is the example of a kind of mature, well-developed use case for SWOT data. But what about something that's a lot newer? So this is more of my own personal work. And what we're going to do is basically leverage some of the philosophies and approaches for measuring remotely sensing discharge from SWOT, and we're going to apply it to carbon emissions modeling. So briefly, rivers emit carbon to the atmosphere by way of turbulent diffusion of dissolved greenhouse gases, in particular CO2 and methane. We're going to focus on on CO2 here. Brief context, right? So this here is our most recent global estimate of the total CO2 emissions to the atmosphere. It's about 2 petagrams of carbon annually. Just to orient yourself, right? That's on par with net ocean and land uptake rates of carbon, and it is larger than carbon emissions from global net land use change. So this is not insignificant. This is a meaningful component of the natural carbon cycle. It's something a lot of biogeochemists are quite interested in, and it's something long-term that folks want to try to better incorporate into global carbon models and global climate models. But again, these estimates suffer from significant uncertainty, and a lot of that uncertainty comes from limited observational data sets to drive these models. And so one of the things we became interested in was saying, can we leverage the SWOT data, try to fill in some of these observational gaps, and try to hone in on some of the uncertainty behind this number 2. So briefly, how might that work? So this is the flux equation for CO2 from the river to the atmosphere. And we can get the dissolved gas concentration in the river from data or from global models that exist and perform reasonably well. But the more interesting term here is this KCO2 term, the gas exchange velocity, or the speed at which this gas diffuses water to air. Decades of work going back to at least the 1950s have converged on this idea that normalized K terms can be predicted from water surface hydraulics. Now, when I say normalized, I mean we're normalizing by Schmidt scaling to remove the effects of gas type and water temperature, so that this normalized term is really just hydraulically driven or turbulence driven, and we can predict it from hydraulics. And so if you're familiar with these kinds of equations, right, what might pop out to you is that these red terms down here, again, are directly measurable by the SWOT satellite. And these 2 orange terms are going to be your roughness and your bathymetry. And we have nearly 2 decades of work showing or developing statistical tools to infer these N and A naught from SWOT data. So what we did is we basically just built an algorithm that solves for this normalized K-term using SWOT data, set up the same way as some of the discharge algorithms using Bayesian inference to infer the unobservables from the observables. And can we do that to improve river carbon emission estimates? We refined it through a proof of concept study. And then what about real SWOT data? A few weeks ago, I finished the first run of this on real SWOT data on 1,000 rivers globally. You get these types of time series of gas exchange parameters, right? So this is on Y is your gas exchange velocity. I'm calling these kind of gasographs, these time series of gas exchange that give us temporal resolution of K in a way that's never before been possible. And the goal moving forward is to couple these estimates with established river CO2 and CH4 concentration models that are estimate these global fluxes of carbon from the rivers to the atmosphere. So just to very briefly conclude here, I think SWOT, all this data, all of the SWOT data is already publicly available. Most of the back catalog has been reprocessed to the current kind of quality levels. And I think we're really in a new age of global freshwater science and hydrology, and we have all these novel measurements that we can use to improve hydrological understanding at large scales. I think the SWOT discharge product is an amazing effort. It's been well developed, it's mature, and it's going to be a lot of use for a lot of folks. But I also encourage folks to think about potential applications of SWOT data in their own work and ways to develop your own algorithms to process and make sense of this data. Right. I presented just one example here at the end of this talk, but I really kind of want to use this as a motivation to get folks excited about doing something similar for their questions that they're interested in. So I'll end it there. Thanks very much.
One second, I need to make Merritt Harlan the co-host so she can unmute. But thank you so much for that excellent keynote, Craig. I apologize for all the Zoom technical difficulties with gray boxes.
Thank you so much, Craig, for that keynote. And I'm also sorry that I left the meeting earlier. My internet just timed out. But thanks, Michael, for doing the streaming of that. Yeah, so maybe we'll move in now to the question and answer period. And I think there's already a couple of questions for Craig that I can read out. So let's see. One of the first questions that we have is, let's look at the responses here. Okay, so the first one I'm seeing is, did I understand correctly that the method to estimate discharge from the satellite data is a mixture of process-based equations and statistical methods?
Yeah, so first off, thank you for having me give this talk. So in a sense, but really these algorithms, the way they work is based off of process-based equations. There's no sort of statistical model driving the predictions per se, but what we are doing is using kind of established inverse modeling techniques to try to limit some of the uncertainty in the equation. And so, you know, I think the best way to think of it is these are process-based equations that have to be inferred through a variety of statistical methods. So.
Great. Another question is, which is a tricky one, so I feel for you, but can you give some examples of why the estimation of discharge with SWOT did not work well? Is it related to satellite data quality like clouds?
Yeah, so I think the thing to stress is that is it very much kind of a work in progress results. And so, you know, we're still teasing out why the estimation might vary in quality, and it kind of pertains to this next question too, where there particular regions where it might be less accurate. And so we're still teasing that out. But what I can say is that it's probably coming from a mixture of, yes, SWOT data quality. So, these measurements that we're getting from the satellite folks are processed to a certain extent, and those algorithms are being tuned. And so the quality varies. It doesn't have anything to do with clouds because this is a cloud penetrating radar. But the other kind of big thing that might cause poor estimation of Q in certain places has to do with this idea of priors and prior bias. So, we're relying on existing data sets to inform how we set these priors in different rivers around the world, but those data sets themselves might be biased or might be missing, certain geomorphic characteristics of different types of rivers. And so a lot of that error in Q estimation might be coming from kind of a misinformed prior. And so, yeah, I guess really the way to think of it is some of it is data quality, some of it is these prior estimates.
Great, thank you. Another question for you. Are the remote sense estimates values of K ground truthed?
If we're talking about the gas exchange K, I assume. Yes, that's tricky. So the data sets that we have for ground truthing K are really, really limited. In small rivers that may or may not be observable from SWOT. And so they're ground truthed in the sense that we have ground truthed the process-based equation behind that algorithm, the equation I showed on the slide. And then we also confirm that, and I didn't show it here, but we also confirm that the remotely sensed estimates reasonably match what we would expect if we ran this with full hydraulic knowledge. So if we were to run the same equation in situ. And so it's not directly ground truthed, but there's kind of two stages of validation. I think it was reasonably certain that it's working, right? But yeah, you're right that it's tricky to ground truth those.
Great, thank you. Another question. Are there particular regions where SWOT outputs will be less accurate? What does uncertainty depend on? Which is similar to your previous question, but if you want to comment.
I can answer the second half is worth talking about the uncertainty question. Yeah, so the regional differences, I think we won't know for a little while until we have more runs, more understanding of how all of this is working. The uncertainty is coming again from measurement tolerances or the measurement error budget that comes from these SWOT data. So even like the water surface slopes have a prescribed, very small, but a prescribed kind of measurement tolerance that introduces a bit of uncertainty. And then the majority of the rest of that uncertainty is coming from the priors that I already mentioned, and with small extent the equations themselves. I believe most of these algorithms, to some extent, parameterize uncertainty in the flow laws that we're using. But so really that uncertainty is coming from, again, measurement error from the SWOT data, a small amount of uncertainty in the flow equations themselves, and that pretty reasonable amount of uncertainty in prior terms. Yeah.
Great. And then we have one question that I think either of us could answer, so maybe I'll take a stab and then let you fill in gaps. But the question is, could the SWOT data be used to estimate inflows into lakes or reservoirs? And that question, the answer is yes, that SWOT can be used to look at connectivity between lakes and rivers. And there's a group of scientists who are actively looking into reservoir monitoring from SWOT. It does require some aspects of SWOT data to do it directly. So you need to have a river that's large enough to estimate discharge, feeding into a lake that's large enough to be observed by SWOT, and an estimate of evapotranspiration, for example, to get at that mass balance. But yeah, there's a huge component too of lake and reservoir monitoring that we didn't highlight in the keynote, but is a large portion of SWOT hydrology as well.
And I'll also say that the proof of concept paper for an algorithm that does that is already out, and we can actually probably do it. But yeah, there's folks working.
Great. Let's see. Another question is, okay, how well have you seen discharge being estimated in smaller streams or creeks? Here in Texas, we have point source discharge in different spots along the watershed. But if this is an option to help estimate discharge in other spots of the watershed, then this would be a great option.
Yeah. We're not producing discharge estimates in rivers below that 50-meter cutoff. And so I guess it depends on what you think is a small stream. I don't think 50 meters is particularly small. And so, I think these data will help at these point sources, and there's various sort of inverse techniques that you might be able to use to get discharge in these larger rivers, and then sort of inverse routing to try to figure out what's going on in smaller, non-observable rivers. But yeah, in general, we're really not looking at least right now, these really small streams.
Great. Another kind of detailed question is when we will get corrected SWOT data with all the metadata assigned. When we access data using Earth Access, then at some station we get more than 2,000 granules. So I think the problem is with the spatial extent. So maybe that question we can kind of table actually for our afternoon data access workshop. But Cassie, if you had any comment on SWOT metadata that's available now.
We're aware that the metadata spatial extents aren't necessarily prime for searching. I think we've got some workarounds for that for different data products, and you can specify the path numbers or the scene numbers to get your exact spot that you want. And you can even do that using wildcard search with Earth Access. So to like really hone in and circumnavigate that spatial extent problem, that's how you would do it. But we are aware that the metadata is a little bit off, and it just takes a lot to correct that because you'd have to reprocess everything. But thanks for pointing it out.
Thanks, Cassie. There's another question that maybe I'll take a stab at from the intro, but Cassie and Craig, feel free to chime in too. How does the Ka band radar interferometer used by SWOT differ from other radar technologies in terms of monitoring surface water? And so something that's unique about SWOT is its use of Ka band, which is a wavelength that is kind of designed to uniquely look at surface water and ocean topography. And also the fact that SWOT has swath-based radars. And so you're looking at elevation returns over large areas. A lot of our nadir looking altimeters kind of just have a line that they're looking across. And so because SWOT has kind of a large spatial footprint on the ground of data that it's observing, it can get at multiple returns of large lake and water body features. But Cassie and Craig, feel free to chime in as well.
I think that's
okay.
a good answer.
Great. So let's see. Another question for you, Craig, or actually for Cassie also, but I'm still new to the SWOT analysis. As a beginner, what difficulties I may encounter while learning this new approach in watershed studies? For context, I'm an ecologist. Thanks.
Yeah, I can take a first stab, I guess. I think one of the unique things, at least about the discharge estimates that we're making, is that they are still snapshots in space and time. Right? when the satellite passes over a specific river. And so if you're maybe used to thinking of kind of watershed science and thinking of this fully distributed and connected river network, that might be kind of a foreign concept. And I didn't talk about it here, but there's ways that we're producing other discharge estimates that kind of handle that and produce these full river network estimates of river flow. But I think that's unique. And then in a much more pragmatic sense, and Cassie can speak more to this, but some of the way that the data is structured is, I think, maybe relatively unique to some folks who work at kind of watershed science and watershed scales and learning how to process a lot of NetCDF files, which you'll probably talk about this afternoon.
Yeah, no, I would completely agree. Sometimes diving into a whole new data set can be really overwhelming, and we acknowledge that. So as a beginner, I would have been like, oh my gosh, what is all this data? How do I even like navigate this? But we do have some tips and tricks and some tools. So I highly recommend diving into the resources I'll talk about this afternoon. But I understand it's a lot. It's okay if you're overwhelmed. It's a new thing. You got this.
Great, thank you, Cassie and Craig. Another question for Craig, but also Cassie again. Was this analysis performed using the beta data, considering additional fixes from NASA is yet to be done? And so in my introduction video, I had said, that SWOT is kind of still being validated, or that some additional, data quality will be looked at in future reprocessing. And so, Craig, if you'd want to mention which version of data, and Cassie, if you had anything to add about data availability timelines and such.
Yeah, this is the most recent. So this is not beta data. This is the most recent processing run, which I believe they're calling version C, but I might be wrong. I think we pulled all this data like a few weeks ago. And so some of the bugs from the beta data set and the beta preprocessed data have been fixed. And obviously there's still going to be more stuff that gets fixed when they put up the next release. Yeah, something I think just to be aware of if you start playing around with SWOT data is be very careful about the version you're using, because it's very new and it keeps getting reprocessed and they keep putting out different versions of the data. So just being very aware and thoughtful of what version you're using and being consistent.
Yeah, right now you're totally correct, Craig. Like it's version C of the data, but in like the short names and how you access the data, it's also called 2.0. So we have letters and numbers. I'm sorry. We didn't talk to each other and we need to do that better. But yeah, so if you see 2.0 or C, you're using the most latest version of the data. And the next iteration of the data will be probably around January timeframe. So that's when the next like big reprocessing campaign is set to come out. So right now, version C or 2.0, you should be good.
Great, thank you, Cassie. Let's see, one of our last questions is, I'm thinking of smaller rivers and streams that may not be observable from SWOT. What's the fraction of global total river and stream surface area that can be observed from SWOT? And Craig, if you don't know this off the top of your head, or Cassie, I'm happy to look it up, but I think there's been some papers that kind of looked at it, but if you know.
Yeah, I don't know.
Okay.
I will say, again, if the cutoff is 50 meters, you're missing a fair bit of surface area. Right? Because the small streams are so numerous that I don't know the number.
Yeah, and I think there is some work to kind of assimilate SWOT data into a hydrologic model that is estimating flows for both small and large rivers. And so in some ways you might be able to use, that data assimilation on their larger streams to kind of feedback what flow might be in smaller rivers. But yeah, and I think for the lakes and reservoirs, it's something like 85% of global surface area might be covered because it will see most of the large water bodies. But in terms of the number, there's many, many small water bodies and small rivers that won't be seen as well. And kind of a detailed question for you, Craig, to sort of wrap up, which if whoever asked this, feel free to elaborate as well, but which optimization algorithm would you suggest for flow law parameter estimation for a Manning-based algorithm?
I don't know. The short answer. I think part of the reason that there are 6 different algorithms producing discharge estimates is that kind of as maybe you're getting at, they all rely on slightly different assumptions, slightly different approaches to the problem. And so there's always going to be scenarios where kind of one algorithm works better than the other ones in different rivers. And so we kind of really stress using the ensemble because it's maybe a little more robust to those idiosyncrasies across different algorithms. And then the other thing too that I didn't necessarily mention here is that each algorithm has different kind of approaches to filtering SWOT measurements and kind of what specific SWOT data it'll actually use as an input. And so there are plenty of different rivers where only 2 or 3 of these algorithms actually run. And so again, if you kind of take this ensemble approach, you get a lot more data. So I don't know if I would recommend a specific algorithm unless there's like a very particular use case.
Great. Well, I think we'll maybe kind of wrap up there for the Q&A portion. But if your question didn't get answered, or if you have another one, feel free to still fill it out into that form. And there's an option to leave your email so that Craig or Cassie or myself could email you with our answer. And yeah, another round of applause for Craig for the keynote. Thank you so much for providing that for us.
Thank you.
Yeah, we'll reconvene at the top of the hour to go into our data access workshop led by Cassie Nichols. And so I hope to see you all there. Anything else, Michael or other organizers? Okay, great.
Maybe that on the website you can find any preparations that you might need to make before joining the workshop if you want to code along. So please have a look on the website.
Yeah, great. And thanks, Rachel, yeah, for the link there. Hi, everyone. Welcome back. We're just going to get started with our SWOT data access workshop here. Great to see so many participants joining at the same time. And yeah, you're able to hopefully visit our GitHub site and click on that README to get access. We did have someone mention that the binder wasn't working for them, but if you click on it maybe more than once or try a minute after, it's a little temperamental, but it should work if you try it a couple times. And yeah, I'll turn it over to Cassie Nichols. Cassie works at NASA. Oh, great. Thank you. Cassie works at NASA Jet Propulsion Laboratory. She's an expert in SWOT data access. She's been part of so many different initiatives and projects, including development of an API tool that we are using at USGS, and it's just been so convenient. But Cassie, yeah, knows all the in and outs of SWOT data, I would say, is just a great resource, has put together so many great resources, and is really an expert for SWOT data access. So I'm so excited to see what she has for us today. And Cassie, I'll turn it over to you. And feel free to ask any questions in the same document that we've posted earlier, and we'll repost. And yeah, feel free to message any of us if you kind of have issues with anything. So yeah, Cassie, I'll turn it over to you. Thanks again.
Great. Thank you so much, Merritt. I'm so excited for this. I love SWOT, and so I'm excited to share my excitement. Okay, let me share my screen. So like Merritt said, if you go on to the GitHub IO site here, Day 2 Remote Sensing, you can scroll down here and go click this link to the README. And that will take you to this GitHub page where we have our Jupyter notebooks. But if you go into this README, it'll tell you like, oh, let's launch a binder. So please, everyone, right now, press this launch binder button because sometimes it takes a while to spin up. So as you guys are spinning that up, let me put this link in the chat too, just so everyone can get that GitHub workshop. And please click this launch binder and we'll see the spinning wheel of like waiting for a while for some of you. And if it doesn't work right away, just try again. Sometimes binder can just be temperamental. But have that out and launched for you. And before we get into any of that though too, I want to remind everyone that to follow along with this, you will need an Earth Data login account. It's just required to access data from NASA. So it's really quick and easy. They never email you. It's like it's kind of a formality. So please, if you do not have an Earth Data login account or you don't know your username and password because it's been a really long time, just go ahead and create a new one or figure that out because we'll need those credentials in our Jupyter notebooks later. So those are the two things that I want you to do right now. If you don't have an Earth Data login account, do it. Go for it. This link right here. And please press this launch binder button. I'm going to be doing this on my local machine just as a safeguard because you never know with binder. And you guys could do this on your local machine as well, but I don't recommend that right now if you haven't like owned the repo and all of those things. But I do have instructions down here if you would like to follow on your local machine later instead of binder. You can literally clone the repo and set up the environment, etc., to be able to do this on your own machine later. So without further ado, everyone has clicked the launch binder and we'll get into that in a second. But before we do that, I think I'm going to give some more context for the data product so that everyone has like a solid background on what we're going to be accessing and opening. This might be helpful for you. Please feel free to ask questions and chat with me about it. But I think this first hour, what we're going to do is I'm going to go into these data products real quick, and then we'll do a couple Jupyter notebooks, going and opening a file from a lot of the different data sets. And then we'll take a short break, maybe like 5 minutes to give people leg room stretch after the first hour. And then the second hour, we'll be diving into more of a science use case. And then talking about this awesome API that my team developed to help make data access for SWOT easier. So that's kind of going to be the structure of these 2 hours. And I'm so excited. I'm ready to do this for y'all. So data products overview, amazing. So hydrology relevant level 2 SWOT products. This is a lot of words. I'm sorry. I just want to like give you a big picture of what's going on here. We have a lot of different data products. And it just goes in order of like, this is like the most raw data up here. And then a lot of the data down the line is derived from this most raw data. So innately, there's like pixel clouds, like pixel points that SWOT picks up with the radar. And from there, it gets processed a little bit. And there's like a vector attribute .cdf from that. And then it gets processed a little bit more. There's a raster .cdf. And then it gets processed a little bit more. And then there's some shape files for rivers and lakes. And then again, process a little bit more, and you got some average over the 21-day cycle that Craig was talking about. And then eventually, hopefully we'll have some floodplain dams as well that come out of SWOT data. I'm going to go into more specifics. There's also different spatial extent formats. So SWOT, it's like an orbit, right? So it comes down in a big swath, which is like a half globe orbit track. I just want to get you guys on the same vocabulary. So if you hear me say swath, it's just literally that half globe of an orbit track, and it's 120 kilometers wide. And then a tile is like a little cube out of the half swath width sort of thing. So 64 by 64 kilometers. And then we have a scene, which is 4 of those tiles put together. So different data products have different spatial extents. Again, it's complicated. And so if you're a little bit confused, that's okay. We have documentation to tell you all of this in our amazing PODAC cookbook for SWOT, which I'll point you guys to later as well. But just for reference to scene number times 2 equals tile number. So if you're looking for a data product as a scene versus a data product that has a tile, they're related in that way. You know, it took me so long to figure that out. It was like embarrassing how long it took me to figure that out. So you guys know now. That's okay. So hydrology relevant level 2 products. We have that pixel cloud I was talking about, lots of point sources next to bodies of water, or not next to, on top of bodies of water. And then we have this raster product that you see here, and this is a scene near Austin, Texas. And this is in that scene format. So pixel clouds are in the tile format, so 64 by 64. And then we have these river vector shapefiles and lake vector shapefiles that come in the swaths along continent scales. And if you zoom in, you just see, oh yeah, there's my stretch of river. Oh great, there's a polygon of my lake. There's file naming conventions. So someone asked earlier, who is like way ahead of the curve right now, about like Earth access and all these things that I haven't even introduced you guys to. But Earth access is an amazing Python package, and I'll get into that in a second. But this is how you can really drill down and say exactly what you want by using like the file naming conventions for the product that you desire. So like there's path numbers, continent codes, tile numbers, and scene numbers, depending on which product you have. And we have a whole table and chart for that on the PODAC cookbook. So please go here. Okay. So I'm going to just dive in real quick on the different data products for hydrologists. So like I said, point cloud of water mass pixels. It's in a tile format. And these have lots of like geolocated heights, backscatter, geophysical fields, and flags. Obviously, quality flags are so important. So look at all the quality flags. Just gonna flag that right now. Quality flags. Okay, and then this is what it would look like. It's very coarse, as you can see. Like this is all points, and this is like just a big tile subset. Okay, and then SWOT level 2 HR Pixie Vec. This is basically auxiliary info for the Pixel Cloud. So the Pixel Cloud is already really big, but they kind of indicated which water body the pixels are assigned to. And so this is a little bit more streamlined in that way, but it's meant to be used alongside of the Pixel Cloud data. I'm not going to go into that very much. We're not going to look into it very much. Okay, and then the raster, geographically fixed rasterized water surface elevation and inundation extent, is that a scene? And this also gives you water surface elevation, area, water fraction, backscatter, etc. And this comes in a 100-meter resolution and a 250-meter resolution. So you can decide which that you would rather have. And then we have our rivers. So there's river reaches. That's how SWOT split up. And a reach is defined as about a 10-kilometer long section of river. And then there's also nodes within those reaches, which have like about 200-meter spacing from each other in a prior river database. And like I said, this is in the continent scale SWOT, and it's going for water surface elevation, flow, width, and derived discharge, exactly how Craig talked about it earlier. So that will actually be in the product later, but it's actually not currently in the product. We're working on the algorithms, getting it all perfect and pretty. Well, not perfect, it won't be perfect, but we're shooting for it, right? And so there's two sub collections for that. There's a reach and a node. And we have the lake, which is very similar to the river in everything. There's like, but the lakes have water surface elevation area, like surface area, and then derived storage change, because if SWOT passes over once and then it passes over the next time, you can see like the difference in elevation and the difference of the extent of the lake or reservoir water body. And then you can do storage change, which is really cool. We haven't been able to do that from a satellite before. And there's 3 different flavors of that. There's observed, prior, and unassigned. And to explain that, it's really a lot better to use a visual. So we have this prior lake database, and that means we've assigned like random IDs to every lake that we know of in the world. But there are definitely lakes that we missed. So if you're like, oh man, my lake, I want it to be in the prior lake database, I'm sure that there's a way that you can talk to the prior lake database people. But right now it'll be captured in the unassigned lakes, and over time we might add numbers to those. So observed is what SWOT would just see as it observed, right? And then prior is, oh, we assigned a prior lake data, like lake number to this water body. That is the water body that is assigned to this section of the river, or not river, lake. So if you see here in the blue, there's like little lines denoting like, oh, that should be a separate feature from each other. But observationally, they've kind of all melded together. So in the observed one, there's no separate lines like this. And that is just a fact of like, oh, sometimes this part of the lake is not connected to these parts of the lake. And so we assigned a different number to this part of the lake. And so the prior file treats it as different water bodies and separates the feature into those 3 different regions right here. But the observed makes it all one. So that's kind of like a big difference there. And then we have the unassigned lake. So if we didn't say that that was a lake, or it's like there's like a random water body out here that we think is water, but it could also not be water. It could just be really, really shiny something that it thinks is water. We capture that in unassigned lakes. That's a little bit, like that's pretty detailed, but I think it's important that you understand like what you're getting into when you pick a different lake data set. And then again, we have river average and lake average. And basically what this is cycle average. And it's like an aggregation of river reach path data within like basin scale. So no longer swaths, but you're looking for the big basin that you have your watershed model on. and that is what you want. Okay. And then, SWOT doesn't just do hydrology, it also does oceanography. So we've got lots of different oceanography data sets too. The big three are the radar, and then nadir altimeter, and then sea surface height. So I'm going to briefly go into these. I'm not, just caveat, I'm not as much of an expert on the oceanography products. I've spent a lot of time in hydrology. So please, if you have like very detailed specific questions, ask them, but I might have to say, I'll get back to you. Okay, so for these radiometer measurements, it's like radiometer brightness and temperature and tropospheric correction data products. There's like the O/I is because it's like operational or interim. So they release different data like at different times. And if you want like the near real time data, the operational, it's within like 7 hours. But like it's not like, oh, we're for sure this is it. It's just like depending on the level of certainty that you want and is which product that you'll get. And there's a nadir track. So along with the swaths on the left and right, there's actually a nadir measurement taken right down the middle of every single swath. And so, yeah, that's a big picture look at that. And then we also have nadir altimetry, operational geophysical data record, and that's on that nadir track as well. And that'll give you sea surface height anomalies and significant wave heights along that nadir track. And there's like an interim geophysical record as well. And that just, again, has to do with the timing of sorts, and when you want your data and how accurate you want it to be through the processing. Okay, we're gonna keep going. And then we have SWOT level 2 sea surface height and significant wave height over the ocean. So there's like a 2 kilometer fixed grid, like big scale, but then also an unsmooth 250 meter grid. So this is what it looks like, which is extreme detail over the ocean, which is super cool. And there's different sub collections. There's basic, wind wave, expert, and unsmoothed. And you can find more information about all of that on our PODAC cookbook that Merritt linked in the chat, and like the handbook, etc. So that was a lot. I'm sorry that was a lot, but I think it's helpful to have that context while we're going into our notebooks. So I'm going to pause there and look at the questions just to make sure that I cover everything. And hopefully you guys went in. If you joined late, please press this launch binder button inside of the 2024 SWOT ECR workshop, and hopefully it'll launch for you and we can go into everything together right now. Okay, let me look at the questions. It says, if I want to work with SWOT river discharge data set at a global scale, what would be the best approach to handle such big data? Any way to avoid use of AWS or get some computing resources from NASA and CNES? That is a great question, and I will go into how to do that. So that great segue, yay! Is there any way to get computing resources from NASA and CNES? I think CNES has like a big high-powered computing thing that they're releasing, but you don't have to use AWS. If you have your local machine, you can definitely use your local machine, and everything that I'm gonna show today can be able to be used on a local machine, but I also have cloud tutorials as well. And then the next question, what would be the best way to access lake data for the whole world? Wow. Well, you could definitely upscale the methods that I'm talking about, but I think later on, in the second hour, I'll talk about hydrocron and how it's not just going to be for rivers, but it'll also be for lakes. So stay tuned for that. And then it says, can the lake shapefiles data product be accessed for an entire continent or global continent swath? I think the lake average product might be better for you for that question. So downloading like all lakes at a continent scale, it's a scale, not a continent scale, but a lot of the times it's just like the SWOT pathways of SWOT, unless you know unless you have like a specific lake ID, which is what we'll talk about later with hydrocron. Okay, I think I'm just gonna dive into this because I think a lot of the questions that you guys may have right now might be answered in the next portion. So if you clicked on this launch binder link, you should see something very similar to this, a Jupyter Lab environment where you have the SWOT HR local machine IPYNB just like automatically launched out like that. You might see some of the other notebooks right here as well. We'll get into that later, but for your viewing pleasure and my screen size, I'm going to close that. Okay, so SWOT hydrology dataset exploration on a local machine. I should note I made all of these tutorials with my colleagues at PODAC, and I'm super grateful for them. PODAC is the Physical Oceanography data center at NASA. It's the NASA data center that hosts SWOT data. So if you're like, PODAC, Cassie, can you say this word? And I do not know what it means. It's just basically the data center that hosts SWOT data. Okay, so we're going into this. This is Python. You do not need to be an expert in Python to follow along here. But I'm gonna just go for it. So Python, there's lots of library packages that you need, but in the binder environment, these should all be set up for you, but we still have to access them. If you're new to a Jupyter Lab environment, I like to run cells by pressing a Shift Enter on my PC. That's how I work. I think you can just press this play button if you like clicking buttons. So that's kind of what I'm going to be doing here. So I imported all of my libraries, and then we have this Earth Data login account, which is where I want you guys to, so for me, I have mine saved, like persisted to my machine. But for you guys, you're going to need a login with that Earth Data login account number, account and password that you either just created or you've had for a long time. And if you don't have one of those, again, just visit this website. It's really quick and easy to sign up, and you'll need that in order to access this NASA data on these notebooks. So again, I press Shift Enter for that, and now I'm all authenticated. Okay, so single file access. Now here's where we use this amazing Python package, Earth Access. It's created by one of my colleagues, spearheaded at NSIDC, which is a different data center at NASA, but it's amazing. It really simplifies accessing any kind of NASA data. It's not just for SWOT, it's for like global sea surface temperature. It's literally like any NASA data set that is hosted at the DAC, hopefully should be able to be accessed with Earth Access if you know the data set short name. So like I said earlier, right now we're at version 2.0 of the SWOT data. And so the short name for the rivers is SWOT level 2 HR, which just stands for high rate river ST and 2.0. So that's the short name for rivers. And then I said, I want to get data. Let's see how many files are between February 1st and July 15th. And then I was very specific. I said, okay, I want it to be a reach file, not a node file. So I added that in my wildcard search. And I said, I really like past 287. Let me grab that. And I want North America. So that's why I had these wildcard searches here. And so if I execute that, it will search this collection for my time period and anything that matches my granule names right here. And I found 8 granules. Wow. When I say granules, that is just another figure of speech for files. NASA just really likes to include new words for us. So when I say granule, that means file. Okay. And so we've got that. We've got our 8 granules. And let's say I just want to access that first one. So I'm going to use Earth Access download and download the first instance of whatever was 8 granules that I found. It's getting the granule, and then I've already downloaded it. So you're going to see a lot of messages on my screen like, oh, Cassie already downloaded it. So, yeah, I did. But you guys should be able to download it very quickly. And then here we're just going to get some of the file names from Earth Access so that we can unzip things. Unfortunately, or fortunately, however you want to look at it, shape files, they come in like 5 different files, right? They're and to post it in the NASA archive, we have to zip them all up. But that just means we have to unzip them all when we're using them. So this is just some processes to unzip things. And in the cloud, there's kind of like a workaround because it's hard to work in the cloud with zip files, but we figured out a way. So if you're like, ooh, I want to work in AWS, we have a version of this notebook that is also in AWS. Okay, so I said, okay, I want my file name and I want to download that and view the attribute table. Let's see what that looks like. And here we are. We have all the attributes that we could ever desire. We have our reach ID, time, different things like that. Lots of variables. There's so many. So feel free to peruse your favorite one, water surface elevation, etc. And down here, you'll see that you can plot like a swath of it if you'd like. I really like this explore function, so I'm going to do this again because I like it. It takes up a lot of like bandwidth in the notebook, but it's very fun because you can like pan around and zoom in and zoom out. You could say, oh man, what is this one? Let's look further. And then it can give you, oh wow, all of the variables. You see right now lots of -999 values for those middle ones of discharge because the discharge algorithms like are still working on the discharge. So you're just gonna have still values for a bit for those. But just letting you guys know. So we can do the exact same thing for the lake vector shape file. And so we have like a short name for our lakes. The only difference from the river is it says Lake SP. And then I said, oh, I want that same time frame and I want my prior lakes instead of like any observed lakes or unassigned lakes. Only give me the prior lakes, those lakes that are predefined in the prior lake database that you could find on links for in so many different things. I should note on our SWAT PODAC cookbook, additional resources, we have so many things for you guys to check out. Is that SWAT data user handbook, features of the data that you should be aware of from our engineers that created the data sets, your latest release notes, different events that could have happened, and a place where you can give feedback on SWAT data or ask your questions to the experts. We also have linked here the prior lake and prior river database. So SWAT river database is SWORD, prior lake database is the PLD. So please go ahead and like find your respective lakes and rivers right there on your own time. But I wanted to mention that that's there because I keep referencing the prior data sets and that's where that you could find them. Okay, did I press this yet? I don't think so. So it's searching for my lake. Oh, look at that. 8 again, because every 21 days we have a pass for pass 287. And there's about like 500-ish passes. There's more than that, but you can find the passes as well on our PODAC cookbook. I'm just gonna keep pointing you guys to this. There's like a SWAT spatial coverage section, and I like using it in the Google Earth desktop application. There's this KMZ file for the 21-day orbit that you can find, and you click there and you can download it and open it up in Google Earth desktop to see where your passes are for your region. And so say I like this pass. Oh, great. Pass 568. That's the one that I'm going to use. So I highly recommend doing that if you want to find your specific passes. But you also don't have to do it that way. You can do spatial search, but like someone pointed out earlier, spatial search isn't necessarily on the top of its game with the metadata right now. There is a thing blocking me from pressing. Sorry. Okay. Okay, so we found that, and we can press download again. I've already downloaded it, but you guys can do that with me. And then we're doing all those file names and zip files, extracting the data, getting the correct file names, and then opening that attribute table. I have a couple questions that I've gotten in the past, like in the chat. So it's asking about Google Earth Engine. Right now, SWOT data is not in Google Earth Engine. And also asking about coverage in the Southern Hemisphere. There is coverage in the Southern Hemisphere. SWOT is a global mission, and it's between 78 degrees north and south. Okay, so it's taken a little bit to read this attribute table, but that's okay. It'll come out. Okay. And this is what it would look like when you plot it. It'll get there eventually, guys. Sometimes it's just a good breather. I've been talking a lot.
Cassie, while it's reading that, do you want us to do a pace check?
Yeah. Yes, please. Okay, it's looking like I'm either just right or too fast. So thank you for your feedback. I will slow down a little bit. Maybe it's good that this is taking a little bit. I'm surprised it's taking so long, actually. I didn't do this yesterday. But here we go. So we have our lake ID. And there shouldn't really be a reach ID in the lake ID one, but there could be if a lake and a river reach kind of coincide. If there's like a lake in the middle of a river, that could be populated. We have different information like that, water surface elevation, etc. And then when you plot it, it would look like this. Sometimes plotting takes a little bit, so I'm just going to skip that. And if you guys want to execute it, you can. But I'm going to move on since we already looked at the river ones. Okay, now we get into the pixel cloud. Woohoo! This one's a pretty intense data set, but it also can be very useful. I'm working on a tutorial with one of the engineers behind the Pixel Cloud. So be on the lookout if you're like, you really want to get into the weeds of it. We're going to be releasing a new tutorial in the next couple of weeks on specifically only the Pixel Cloud data. But again, we have our short name for Earth axis that we use for the Pixel Cloud. We have our temporal search. And this time I was like, I'm going to do a bounding box because the metadata for the Pixel Cloud through the raster is a lot better for bounding box searches. So you find 229 files of tiles for the pixel cloud for this one lake near Austin, Texas that I randomly picked. So we can download that first result. And then since it's not a zip file, it's a netcdf file, I can just open it innately with Xarray, which is another great Python package that I use quite a bit. And I like Xarray because it opens up your different categories, etc., and it tells you what everything means. So like there's this classification flag, and so it'll tell you like, oh, when the flag value is 1, it's land. When it's 2, it's land near water. When it's 3, this is, etc. So that's very helpful. And you can go into that with any of the data variables that you want. So I really like Xarray for that ease of access and knowing what you're looking at. But obviously there's so many variables, guys. So if you want just like a quick plot for plotting pixel cloud using like classification and quality flags, we have a mask to get good water pictures right here. So it says so DSPixie is what I am calling what we open the netcdf file in and what that Xarray data set is. So right now, right here, I'm just saying, hey, where this classification is greater than 2. So if we look back up here, I said I opened up the classification one, right? So we don't want land or land near water. We want all the water. So if it's greater than 2, so we're getting rid of those first 2. And then here, we have this geolocation qual. Oh, let's go look at what that looks like. Okay, I just have to find it in this list. Oh man, I forgot where it is. Geolocation qual. Where are you? Did I pass it? I think it passed it. Guys. I should have practiced more. It's fine. Here we go. Okay, so there's lots of different quality flags right here. So layover, phase unwrapping, all of these like fancy terms that you can find out the really nitty-gritty information in our handbook that I pointed to in the cookbook. When I first did this, I asked like the engineer behind the Pixel Cloud what he would do, and he said anything less than 4 is good. But because of how SWOT data is right now, it's kind of over correcting a little bit, and it says a lot more things are suspect than actually should be suspect. So I wanted to keep in all the suspect quals as well. So that's why I picked the value that I did down here. But later on, like in the next data processing, if you have this less than 4, that should be okay. But I picked the bigger one because I wanted to get all of these suspect flags instead. There's like 4 levels. There's just like normal, there's suspect, there's degraded, and there's bad. You don't want to use degraded or bad ever, but suspect is like kind of like it's a little okay, but we can use that. Okay, so that's what I'm filtering out. And then I plot the DS pixel cloud, longitude and latitude, and the height. That's what I wanted, the height and based on the mask that I have. So I'm getting all the suspect or better pixels for this. I should have run this and then talked a lot. Sorry, guys. Oh, it'll come, well, you saw what it looked like, and you probably already see what it looked like. But I can explain the next one as well. So we have the water mass pixel cloud vector attribute in that CDF. And that's like the pixie vec. And let's say I want the exact same cycle, path, and tile as previously downloaded. So I want to match my, I'm gonna click that. I want to match this file exactly that I got. So it told me I downloaded this file right here. And in the file naming conventions that I talked about earlier, this is the cycle, this is the path, and then this is the tile number. and it's the left swath. That's what the L is for. And so I said, oh, okay, let me grab that. And I am going to put the exact same number right here in the granule name. So it gets me the corresponding pixel vec attribute as what I just did up here, and it plotted. See, so these are all the water pixels that it found in this region. A lot of water, guys. Okay, we can do the same thing for the Pixie Vec results. And you find a granule. I just found one, which is exactly what I was expecting because it's just one cycle for the specific path and the specific scene. And I could download that. And then I can open it up using X-ray. And that same thing happens right here. You can open and close and look at the different dimensions and what's available here. And a simple plot. And this is what it looks like. I'm going to run it again, though, just for posterity's sake. I've got a couple specific questions in the chat. It asked, in the water pixel file, there's so many variables per point. Which one do you suggest to use to correct the measurements on height and extent on a lake? I think I just went into that a little bit more. But yes, there are so many. But those like classification flag and the geolocation flag, those are a good start. But there's like an overall quality flag as well that is helpful to use. So be sure to look at all the documentation on that. And then, okay, here we go. Here's our pixel deck. It just assigned all of those pixels to the specific lake bodies or river bodies that it found in the area. And there's my pixel cloud. Okay, let's do the raster, the final one. So this one, I decided I want the same cycle and path as previously downloaded. And I gave it a bounding box as well because bounding box is working pretty well for the raster data set as well. The bounding box search just doesn't really work necessarily as well for the vector shape files, just the nature of the metadata as you guys pointed out, but it works fine for the pixel cloud and the raster. So if you want to run this, and I also pointed out I want the 100 meter, not the 250 meter as well. And I expected it to only find one granule. You can change all of these. You can specify by time, different region, different granule name, especially so if you want to search by time or a different region, definitely get rid of this granule name. Just hashtag it out and it wouldn't show, and you'll get results that are a lot more for your region of interest, but this is just for example's sake. We could download that and open it up using X-ray as well. And it'll show you all the different variables as well. And there, for this, there is actually, so like a water surface elevation, and then a water surface elevation quality flag, which corresponds with it that you could flag. So like I said earlier, there's good, there's suspect, there's degraded, and then there's bad. So there's 0, 1, 2, 3. And then we have like a full-blown tutorial in our PODAC cookbook for this specifically. So we have a SWOT, raster, multi-file access, and quality flag application in the cloud or locally. So whichever one that you want, it's right here, fully rendered. My colleague Nick made this notebook, and it shows you how you would visual multiple tiles, create a time series, and then like also do a quality flag application towards the end. So if you're interested in that, this is a great place to go for that. Okay. And then, oh, HV plot is looking a little bit fishy today. There is a warning. Okay, that didn't happen yesterday. Sometimes these things occur. I'll see if it goes quickly or not. Oh, wow, it is being very temperamental. It says there's name value. Amazing. Well, you saw in the Podak cookbook that it should look something like this. And it is fully rendered. It's probably some dependency or another that changed with HV plot recently that I haven't updated. But yeah, so we'll keep it at that. Wow. Okay, so that was the HR data set. And so I'm going to close out of that. Well, actually, before I close out of that, any lingering questions on the hydrology product that I outlined here? Someone pointed out that the estimated storage change is only in the prior lakes database. And why is that? Well, it's just easier, I think, when they decided, because when you actually have an ID to associate a storage change with. And so the unassigned lakes don't have their own specific IDs, and that's why it's in the prior lake database. And then the observed file, it's a little bit different because if lakes merge together or things get a little bit merged and it's all said as water, it's a little bit difficult to parse out what storage change is associated with what portion of the lake. And so the prior lake database option for the lake files is the one that has storage change. Okay, so I'm going to go into the oceanography one next. So if you want to click along with me, you can open up the SWOT oceanography local machine in your environment in Binder. You just click on the side if it's there for you, and you can say SWOT oceanography local machine. I'm going to close that up again. Okay, so this one is going to show you how to access SWOT level 2 LR SSH data and then nadir altimetry data, SSHA. We're going to do the same thing here. We're going to import some libraries. We're going to do our Earth data login again. Okay, that's okay. Earth data login again, you'll probably be asked for your credentials again. There is a way when you do this on your local machine to persist your credentials, but in the in the Binder environment, it doesn't make sense for you to do that because it just doesn't save for you anyway. So later on, when you do this on your local machine, you can say persist equals true, and it won't ask you ever again if you're using your same machine. Okay. So that should go for it. And now we can search and download the data. So just like previously, I gave it a short name. I'm giving my timestamp that I want it between. There's lots of files over the ocean. It's so many. So to just get like 10 files, I grabbed right here just a very short time period, and I asked it for expert files. And there's different sub-collections. There's basic, wind wave, unsmooth, and expert granules for that. And this time I said, why don't I just download all of them? You don't have to just pick one. You can download a set of them using Earth Access as well. So I downloaded them and I said, okay, let's use Xarray to open up all of them and combine them in a nested way and concatenate them along the number of lines. and it's going to open up this data set. This one might take a little bit because we're combining all 10 PDF files into one. But here we have our dimensions and our data variables as well. If we click here, again, there's so many data variables. And to really understand all of them, this is a good first look when you're looking at the metadata, like, what does this mean? But if you want more documentation, you can go to the handbook of the SWOT data. And the oceanography data set is interesting because what they do is they have this height crossover correction. So you actually have to apply this yourself. If you just plot the SSHA or sea surface height anomaly for the Karen data set itself, it'll just give you like lots of colors that are not necessarily correct. There's this crossover correction that needs to be applied. So I has to make my SSHA Karen corrected myself. And that's just how the data is structured. I apologize. It's just a lot. And you can plot this. And it'll give you the 10 files over your chosen projection. If we plot that corrected value. Okay. They said they're getting a warning that they've used 1.73 out of 2 gigabytes on the binder environment. Do I need to clear / how do I clear? Oh no. One of my colleagues online, can you Google how to clear binder environment? Thanks.
Yes. And I think if it's not over, it's still okay. But we'll do some digging.
Thank you. If you want, you can also go back into the data downloads, that folder that should have appeared, and you can delete old files because we won't be using those again from the hydrology product. Okay, so it plotted. Here we are. I didn't zoom in, but if you, you can zoom in a little bit. It won't change the resolution, but there we go. There's also a question in the chat. Can we access the data the same way presented here for both CalVal and nominal phases? Yes. The CalVal period is available via Earth Access as well. It's just depending on the dates that you select. So the first 3 months of data that is available for SWOT is the CalVal 1-day repeat orbit phase, and that is available via Earth Access. And then the next question that is here is, let me make it so I can see it easier. I understand SWOT is designed for water observations, but I would like to know if the pixel cloud might have correct values height for non-water areas. I am not an expert in that, but I would say it's probably not it's really not designed for land. So I would not trust anything that it says over land. I would just trust the water. But you can probably go into some weeds for that and look into the handbook and see what happens. Okay, so next we're going to do the nadir altimeter. And this is just the search that I did. And you know what, just for like size, space, and this is basically identical as the one previous. I'm not going to run this. I'm just going to show you guys what it looks like. And I did depth or elevation for this one. You don't have to run this as well. So yeah, I think with that, let's do like a 5-minute stretch break. Give time for people to write questions in the chat that I could answer at the top of the hour. But we'll pause here and I'll start again at the top of the hour. Thanks, everyone.
Thank you, Cassie.
Okay, and we're back. Hopefully you got some good stretching in, you got up, walked around. Amazing. Okay, everyone. So I just want to point you again to this SWOT cookbook. I cannot emphasize this enough. A lot of my colleagues and I have put lots of hard work into this, and we want you guys to use it. Tutorials on how to use SWOT data. And let's get back to our Jupyter Hub environment. So before our break, we looked at the HR and LR, so the hydrology relevant and oceanography relevant data sets. I'm going to close those out because we won't need those anymore. But the next one that we're going to do is this SWOT HR science application local machine. So if you double click that in your Jupyter environment, and if you're running into those like errors like, oh man, I've used a lot of the gigabytes in the binder environment, I think what you can do is you can just like shut down the kernel for the specific notebooks that we've done in the past and then delete the old SWOT files in the data downloads folder that we created, because it won't let you delete it if it thinks you're using it still. So that's why you might have to get rid of like the old ones. Like, I'm not using this anymore, so I'll shut down that kernel. I hope it's the same way in binder environment and the dot will go away if that's how it works. So that might be what you need to do to clear your cache, etc. from the last hour so you can delete old data. Okay. Okay, so I'm going to close this again, and I am going to go into this amazing tutorial that my colleagues created. So this is SWOT Hydrology Science application tutorial on the cloud. And this can be run on your local environment. And there is an AWS cloud version of this notebook, and you can go there as well. But again, you'll need an Earth Data login. And it's meant for version 2 data or version C data, whatever you'd like. But Arnaud and Jeffrey created this notebook. They work at JPL as well. They're postdocs there and they're amazing. They did this back in February and I've just modified it a little bit by bit. But what we're going to do in this notebook is we're going to retrieve some hydrological attributes on river reaches, and we're going to query the reaches by river name, downstream tracing ID, upstream tracing ID, and then we're going to plot the time series of those water surface elevations. You can do different variables as well. And then also we're going to do some like river longitudinal profiles and watershed analysis here. Really fun. Let's dive into it and we'll do lots of really cool visualizations. So again, we're going to have to do some import packages and authenticate via Earth Data login. So we've got those two things out of the way. And this is where it gets fun, you guys. Okay, we're going to pick some rivers. So I'm going to show you guys the sortexplorer.com. We have Sort Explorer. This is where you could find your different rivers that SWOT can see. And I randomly decided to pick a basin on the East Coast of the United States. So basin 73 is what I want, and I clicked it. And so what I'm gonna do right now is I'm gonna do this notebook twice. And I'm gonna show it with the basic things that you guys already have, and then I'm gonna pick a completely different watershed and pick that one, and you guys can pick a completely different watershed as well alongside of me, and figure out if it works in your region. So I picked the Susquehanna River just because it looks fun. It's kind of like a cool little shape here. I really liked it. So that's the river that I'm gonna look at, and you can see here there's like different river reach IDs based on the reach that it is. So if I click on one portion, it'll say, oh yeah, that's the Susquehanna River. Here's my reach ID for that section. And this is the reach upstream from it, downstream of it, lat and long. It'll give you just like the very basic information for it. And yeah, so that's what we're going to be looking at in this notebook. And I found the path numbers that go over the Susquehanna River. And how I did that was, like I mentioned previously, I went into my PODAC cookbook, which has lots of information, and I downloaded the KMZ file for the Science 21-day orbit. So I clicked there and it downloaded straight to my machine. And then I opened up that file in Google Earth Desktop, which is right here. And I decided, okay, let's go find the passes for the Susquehanna River. And I zoomed in to that region. Oh man, it's going to test my geography knowledge right now. I need to remember where it was. Let's go back to this. It's near New Jersey, Maryland, Philadelphia. So basically this region right here in Pennsylvania. That's where I'm looking. So I see Pennsylvania. I'm like, oh, okay, great, Pennsylvania. It's probably around this area. So I saw, oh, past 48. Past 48 goes over that region that I want. Great, let me get that pass. And then, past 369. That goes over the region that I want. And that's how I discovered which passes that I want for this data. So I go in here and I entered that. Oh wait, so I did the, okay. We're gonna trust my old discernment because I was just really looking from a very broad scale last time. So past 354 and 091 probably be the correct one. And then enter the continent code. So there's a different code for each continent. So like Africa, North America, Europe, oh, SI, what is that again? I don't remember. But you know what? I think Siberia, etc. So this goes in and gets all of the granules or all of the files from Earth Access that go over this pass number and continent code in my temporal search, and it uses like programmatic like loops to do that, and it appends all the links that I want to this links list. So I'm going to execute that, and again, it's going to search over each pass. So for P in a range of passes, so that first pass 354, it found 5 granules, and then in the second pass 091, that's what it's working on right now. It's gonna say, I also found 5 granules of past 91. Amazing. And so we can look at that links list to see what links that we are downloading when it gives us that. And these are the links. These are the data that we want. And it gives me that river SP for each cycle. So you can see it's like cycle 10, 11, 12, 13, 14, which is exactly what we expect for those first 5 files for past 354, and then does the same exact thing for past 91. Okay, and then I can Earth Access download those files. And it says, oh, Kathy, you did this already. But you guys have not done that already. So it'll take a little bit longer for you, but it should still be fairly efficient. And then we have to do that funny thing where we unzip the files as well. So that's just what I talked about last time. And then we can initialize that open zipped file. And here, it's looping through all of the granules that we downloaded and appending them to one file. So that's super helpful. Well, reading them all. And then here we're aggregating the unzipped files into one data frame. So it's using a geodata frame, and it's concatenating all of the shape files that we downloaded earlier. So this might take a little bit more time, but it's worth it. How are you doing, everyone? Good. Amazing. Yeah, we're concatenating like 10 files right now, so that could be kind of a lot for a machine. And we'll see how it spits out. Mm. Like always, if you have any questions, feel free to post them in that link that they sent, and I'll hopefully get to them. There are Central America river data on the website. There should be anyway. If you look, oh, it's, yeah, North America. North America. Let me just go back to the main one. It'll open up again. Come on, map. Here we go. And I should note on this site, the reach geometries have been simplified for map efficiency. So if you see the center line of the river doesn't totally match up with what you're seeing, that's okay. But if you downloaded like the Sword River database or the actual SWOT data, you'll see a lot more fine scale resolution. Oh, sometimes people name South America to Central America. Yes, there is South America. You can click right here and you're like, ooh, South America. But yeah, South America right there. Okay, let's go back. So it combined all of my shape files that I wanted into one giant geodata frame in GeoPandas. And I've got my reach ID, the timestamp, water surface elevation, slope, all of my attributes I could ever want. Which is so many. I'm not gonna make you guys dizzy with going through all of them. But I have all those reach IDs, and you can see here that sometimes the reach ID is happening a couple times, which is good because we used multiple dates, and we're expecting to have the same reach multiple times. So we can explore the data set here. So we can look and we're saying, oh, wow, the available rivers that I have here, is my river in this data set? Where is my Susquehanna River? Right. Okay, I see Susquehanna, but that's north. Okay, there we go. Right here. Oh, wow, amazing. It has the river I'm interested in. And now we can filter by that Susquehanna River. And here we are. It shows you from the main stem, well, anything that's labeled inside of the Sword River database as the Susquehanna River, it shows up right here. So let's do some river longitudinal profile tracing downstream, given like the start of the reach, using the reach ID downfield. So we've got to do a dictionary in the very beginning, and this code is brought to you by my colleagues because they're amazing. I didn't write this part. And then I picked up from the Sword River database in North America. I looked at my river and I said, okay, the most upstream headwaters of the Susquehanna River, it has a reach ID of this. You can find that either on what we just did as well. You can say, oh, this one looks like the most upstream. That is my reach ID. And I can grab that and I could put it there. Or you could look at the Sword River database and just find through there. And we'll do that in a sec when we rerun this with the whatever data sets that you guys want to, whatever section of river you guys want to do. But for right now, trust me that this is the correct most upstream reach. So we're going to execute that. And then do a downstream tracing. So it got from the very top and it downstream traced, so it doesn't have those tributaries anymore because we're downstream tracing where the water's going. We got a question of, is there a way to submit river names for reaches that come up with no data for the name? Unfortunately, not at this moment, but SWORD is being consistently updated. So if you find a river that you're like, oh my goodness, this is my river, I want this to have a name on it. That's helpful because it's honestly it's very hard to make a global river database and have the correct river for everywhere all at once, everywhere, like, and the correct names that people use. And so to be helpful for the SWORD developers, there's this handy thing that you could say, you say report reach. And then you can put in a request of like, hey, change this thing. I want this name to be on here. This is the correct name for that portion of the river. And you can report the reaches for them. So if you have a very specific region, and we're all really interested in different parts of the world. And so this could be very helpful for our team too. So if you find that your river has no data, please go ahead and report the different reaches that you have that you want to see your river name. Okay. Also, I want to note, just when we are doing this live later, when you're just picking your own reach, sometimes the SWORD River database isn't connected all the time. So like if not all of your data appears, if not the whole river appears, that could just mean that we have like a little bit discrepancy. So if you see here, does this show everything? No, okay. Like when I did this for the Connecticut River, I was like, oh my gosh, this one reach has no data in the reach ID up attribute. That means I can't do upstream tracing because it references that variable right there. So I had to go in and report a lot of the reaches. And it's not going to be innately, so just because you report the reaches doesn't mean it's going to show up the next day in SWORD. It'll happen with the reprocessing campaign. So you might have to wait until all the data is reprocessed again to see that specific name. But there are definitely different workarounds, and you can figure out how to do it without the river name. It's just, I wanted to show you guys one way that we figured out how to do this. Okay, so we can do the same thing at doing upstream tracing. So we run that code, and I found the most downstream outlet reach ID for the Susquehanna River. I did that, and then filtered my download data by the traced reaches. And here, since I did it at the outlet, I get all of the tributaries that come out of it as well, which is really great. So not just the Susquehanna River, but we have this awesome, I can't pronounce that. I don't know how the locals say it. You know what? I shouldn't have even tried. But the west branch of the Susquehanna River, north branch, you know, different things like that. Okay, now let's do some profile plotting. So visualize and plot a time series of water surface elevation. Oh, sorry, excuse me. Width and slope longitudinal profiles. So I wanted to retrieve all possible acquisition dates and get some trace time. This is just some code that we got to do this. And we're going to explore what variables that we can do that I want to choose. So look, there's water surface elevation, there's uncertainty, different things like that, slope, width. These are all the variables that are associated with these four terms that we found. So let's say first I want to do a water surface elevation. I can run this code and it'll plot the longitudinal profiles for all of my dates and the downstream distance from the outlet and the water surface elevation over that entire Susquehanna River stretch. And we are. It's pretty cool. Longitudinal profiles are right there. And then we can choose a date and we can visualize ourselves what that would look like over a period of time. So we have water surface elevation up here, 128. This is what it looks like visually. We did plot this earlier as the profile. Yeah, so I am going to invite us to do this entire notebook again, but for a different region of your choice. And this is dangerous because we might run into errors that we inferred that are in different regions. But this is a great exercise because if that means you're really interested in that specific region, then we should get Ford fixed in that spot, right? So that's why it's kind of dangerous, but we're gonna do the same. Okay, so I am going to look in Sword for another river. So let's say, I'm in California right now because I am in California. So I'm gonna go to basin 77. That is gonna be my choice. You guys can choose whatever basin your heart desires. And we'll see if it works. The other caveat here, though, is that, oh wait, that's not, yes, it is, it's good. The other caveat here is if you want to find the path number for your specific basin, you will need to download the KMZ file and Google Earth Desktop. But for the first couple people, I could do, and you're like, I don't want to do that. If you write it in the chat, the region that you want, I might be able to help you out too. That could be a fun thing for the first couple of people. But for me right now, I say, okay, oh, look at this cute little tiny spot right here. Let me go look in California. I want to see what this river is. Oh, it's by Eureka. That's fun. Yeah, what is this called? This is called the Eel River. So I'm going to pick the Eel River. That's going to be my choice. You guys can choose the same river if you would like. You don't have to do your own river, but I'm going to pick this one. Okay. And I have the Eel River. What do I need to change? So I'm going to find the path numbers associated with the Eel River. So path number equals, and I'm setting that up, and I'm gonna hashtag out the old path numbers. So let's look in my Google Earth Pro and find the Eel River. Okay, it was next to Eureka. So let's see. Ooh, sorry guys. The zoom in this is kind of funky. I'm not used to it. I think Eureka is close to here. Yes, Eureka. So this path and this path would be great numbers to pick. So I have path 302 and path 039. So I'm going to put that in here. Path 302 and path 039. So those are the ones that I'm going to pick. Okay, so Northwestern Alaska is what I got a request for. The West Coast by, oh gosh. Okay, let's zoom out of this. I need to do better at that. Okay, Alaska. Let's go find Alaska. West Coast by Kotzebue. Northern. This one? Right, more northern inlet visible on the coast.
I think near like Bethel, if you see that.
Okay, near Bethel. Okay, thank you. I'm not very familiar with Alaska.
Oh,
Okay,
no, above Nome. I'm wrong. Sorry.
above no. Okay, okay. Above no. You cannot find the SWAT pass number in SWORDexplorer.com, unfortunately. Okay, so above Nome, the codes of view label is there. This is like a search and find sort of situation. I don't see it. Oh no.
Oops.
Do you guys see codes of view? To the right. Okay. Okay, left. There we go. Amazing. Thank you. Okay, so for Alaska in this section, past 99 should have something. And depending on where else you want it, maybe past 562. It depends on if your thing is over here or not. If you want this past number as well, it is past 248. Okay, so you got those. I'm gonna do one more or two more. If anyone's in the KMZ already and you're like, oh, let me find that for you so we don't have to watch Cassie struggle with geography. That'd be great too. But if you don't, that's okay. River Juba in Somalia. Wow, that's really gonna test me. Oh wait, did someone else do it first? Oh, I see. Someone asked first for the River Elbe in Germany. Let me do that one first. Okay. I think I'm gonna zoom out a little bit more. I should just zoom out even more. This ocean's gonna get me lost, right? Okay, here we go. It doesn't orient the same way all the time. Okay. Germany is this way. Wow, it just keeps going. This. Okay, I wanna straighten this out a little bit. There we go. Germany. Can you tell me what part of Germany your specific river is in? QGIS is not very great at opening this TMZ file because it's pretty big. So I recommend Google Earth Desktop. East Germany, flowing into the seas. North Seas at Hamburg. Okay. Hamburg. So right over here. Or up here. I'm just gonna say a couple past numbers. So this one right here is 335. You know what region that you're interested in the most. This one's 458. This one is 29. That'll give you some points there. If you want this one, it's 152. Amazing. Okay, I think for time's sake and just moving on, I'm gonna keep going, but there are ways that you can find out. Oof, we're gonna do that later. Okay. So for me, I found my Eel River passes and it found 3 granules during that time and then 6 granules during that time for the different passes. So this is my links list and I'm gonna download files to the downloads folder. Say, oh, Cass, you already did this. Yeah. We did. And I'm gonna unzip them. And do this again. It says, could it be that there are 0 granules even if there are passes, or am I doing something wrong? It depends on the time frame, or ooh, it might be, is it above 78 degrees latitude, longitude? If it's above 78 degrees, that seems pretty high where we were looking in Alaska. I wonder if SWOT data is up there. No, it's around 65, 68. Okay. Maybe the time frame that you're looking, you might I would try expanding this temporal portion and then seeing what happens. You will also, depending on where you are, you might have to change the continent code. And actually that might be, Alaska might be a different continent code. One of these.
Yeah, maybe AR for Arctic, perhaps, but
Yeah, it says, yeah, AR is North American Arctic. Okay, thanks. Troubleshooting live. And okay, I'm gonna combine my unzipped files into data frame. So I have my data frame for the Eel River. And I want to say, okay, what river am I looking for? Oh, look, there's my Eel River that I'm looking at. Woohoo! And then I am going to change this. So it is now going to say Eel River. And look, it's beautiful. It got it. Okay, what's next? Well, I gotta run that again. And then I need to add on to my dictionary, my river right here. I am sharing my screen. Do you not see my screen? Someone said that I wasn't sharing my screen. Can you guys see my screen? Yeah, okay. Awesome. So let's go. So Eel River. And then I want to find the most upstream reach of that. And I'll go look in my Sword River database, the most upstream reach that I see. Let's do this nice little green one. Sometimes I have like tiny reaches at the end of it. That's just for like processing purposes. So I wouldn't ever pick the end tiny reach, just FYI for you guys. But I have my reach ID right here. Ooh, I don't want to copy everything. I'm going to copy that. And then I'm going to put it here. And hopefully that'll work. And here we are. It got me it. Woohoo. Now we can do the downstream. And again, if not all of your data appears, if let's say the Eel River had like a thing where that downstream up ID wasn't necessarily there quite right, or something was disconnected, you can always change it in the SWORD database and report it. Okay, so we can do this again. And I'm going to put my Eel River. And let's find the most downstream one. Reach ID is this. Copy that. Paste it in here. Someone asked me, why do I use big quotes for the name of the river and just these kinds of quotes for the dictionary? You know what? I don't know. I could probably use either of them. I think quotes in Python are very just that. We could try it. We could try it right here. See what happens. I think quotes are just quotes wherever you go for Python. did the upstream tracing. So we got this tiny little tributary right here, the South Fork of the Earl River. And we can do some profiles. It already knows we want water surface elevation. And let's see. Oh, wow. There's some pretty spiky things right here on those particular dates. I wonder if there was a big outflow or a rainstorm or something like that downstream, or maybe a release of a reservoir or whatever. I don't know what's in that area. So that's something that you could figure out and discern. And you can map out a specific date. And I've got here like, wow, amazing. My water surface elevation is different going downstream, which is what I expect. Great. Okay. So I'm going to move on to this really cool tool because I want to make sure you guys hear about this really cool tool. Actually, let me pause for a sec just so you guys can digest. It's like, oh, wow, we're going to move on to something new. Amazing. So I hope that that was really helpful for you and you found some fun ideas for your own research or your own work that you can dive into more applications. And this is just one of very many applications that you can do. And you can take this code and transform it, run with it, do something else with it. That's what code is meant to be shared. We do have a DOI for the entire cookbook. And so if you go to like this Podax page, we have our Zenodo DOI right here, so you can cite all of our code. Should point out that. Okay. So I'm gonna close this actually, and you could. So right now I'm gonna go into Hydrocron. There is a SWOT time series example notebook in this one, but I'm not gonna do that right now. This is just like the heavy duty, like, wow, if I want to use Hydrocron for so many reaches, this is a way that you can do that. But I think I'm just gonna go over what Hydrocron is and the logistics of it so that we can leave some time for some questions. So Hydrocron came about because Merritt and I were talking at a SWOT science team meeting a couple of years back. Maybe it was a year ago, I don't remember. Yeah. We were like, man, it would be really useful if I didn't have to download all of these shape files all the time. If I just wanted a very simple point, if I like this portion of the river, give me a time series, right? And so what Hydrocron does is it repackages the hydrology data sets from SWOT into like a CSV or a GeoJSON so that you can literally just input one river reach ID from that stored river database. So any of these river reach IDs that you want, you can input that and output literally a CSV or a GeoJSON of just that time series of any of the variables that you want. So instead of downloading all of the shape files for every single path in your region, it already parses out from your ID what path numbers there are, what everything is. And you can do this programmatically. You could do this in a web browser. So I'm going to show you guys like this examples page. Let's say I want to get a time series CSV for a river reach. And you did put this in the group chat. Yes, you did. Great. So I clicked on examples over here and get time series CSV for a river reach. And so literally, if I just copy this entire thing and I put this in my browser, it should spit out a time series. And here we go. It's a time series. And it looks a little bit messy, but that's just because it's a CSV. But lots of people are used to CSVs for like the USGS. USGS uses CSVs all the time, and that's how you get your hydrology data. So this is a very familiar format for a lot of us. I mean, I started with CSVs, right? I didn't start with NetCDF files. I was like, what is a NetCDF? And so this is just a really easy way to do that. And you can change it up here in this location. So this is where the feature ID, that was where you would put your reach ID. So let's say I want to do this one that I copied previously. I'm going to copy that again. Say there's like a region of interest. I'm really interested in that spot. So I'm gonna put that back in there. And I still want the start time to be the same, end time to be the same. And it gives me my reach, time string, water surface elevation, slope, and then it gives me the units for those as well. So it's giving me the WSE right here and the slope right here for every single time. And you can also do that in GeoJSON format. And output, I think I just changed this to GeoJSON. And it gives me a lot more information because it gives all the geometries as well. But there's a way to parse it so that the geometries are all included. Oops, sorry guys. If I want the GeoJSON, that's what the return would look like if you returned it in a very pretty way. But you can also condense it a little bit. So we have some tutorials on the side on how you would use this and how it works, and some examples of displaying a river reach on a map with GeoJSON, and how you do that programmatically. So you literally don't have to just do a browser, but there's also different fields that you can say. So we only output like reach ID, time string, we only do these 5 fields, but you can either eliminate some, say you're not interested in the geometry, you already know where it is, you can get rid of that, and so your fields would be smaller. But there's also lots of different fields that you could do. I think it shows at the bottom here, or even the time series endpoint. I think actually maybe it's here. Time series endpoint. There's lots of behind the scenes data sciencey things. So if you're really interested in data science, like accept headers and things like that, this is for you. You can also use this API behind the scenes on the dashboard. So if like the USGS, where Merit works, is creating a WISP water information from space dashboard that'll be available to the public, so that you could see SWOT data alongside of the USGS gauge data in the United States, which is really cool. And it shows you the format of everything that's needing to be input, the different codes, how you would relate to it, etc. Here we go. Here's all the fields that are possible. So there's so many different fields. But like I said earlier, discharge isn't out yet. So all these discharge ones will return -999, but hopefully in the early next year, 2025 is what I've been told. That should be more populated, etc. So with that, I think I'm gonna leave time for questions. I'm gonna stop sharing my screen. Any questions you guys have?
Yeah, a quick virtual round of applause, Cassie. That was so great, and I learned so much.
I'm so glad.
Yeah, I'm happy to, oh yeah, moderate if you'd like to as well.
Yes, please go ahead, Merit.
Yeah. Let's see. We had one kind of lingering question that is a tricky one, but in the Q&A, someone had a question of, okay, it's actually a recent one. A river I expected to see in Sword Explorer isn't there. Is it possible it will come in the future?
That's a great question. It depends on the width of your river. So right now, Sword encompasses rivers probably 100 meters wide and greater than that. So if your river is like smaller than that, it probably won't be in the river database. So it depends on what you mean by expected to see. But we are noticing that SWOT is actually getting better than we anticipated. So we've seen rivers on the order of 20 meters, but depending on the algorithms, we can't necessarily process that 20-meter width from the pixel cloud into the river vector. So maybe in the future, as reprocessing comes out in that specific file, then you could see extensions as they improve Sword. But right now, the pixel cloud would probably be your best bet. Going down to the pixel cloud level instead of these vector products. The pixel cloud is a little bit more, there won't be discharge for the pixel cloud. You'll just get water surface elevations and stuff like that. But like I mentioned earlier, we are putting out a notebook on how to aggregate the pixel cloud into like using the algorithms from the the algorithms from generating the products. We'll put out a notebook tutorial on more specifics of the pixel cloud soon.
Awesome, thank you. And there's a couple of rivers in Sword that are in the 50 to 100 meter, but yeah, as Kathy said, it is limited by size. Okay, another question that we had come up from before is, I believe I've heard it mentioned elsewhere that SWOT might have a way of capturing ice thickness. Is that true, or did I dream it? If true, what DAC might be most useful for this data?
Ice thickness. No, we're not going to be able to see the thickness of ice ever. SWOT doesn't see the depth of water. It just sees the surface height. But I know it has been detecting ice. There's like ice flags, and it's really promising. Like some of my cryosphere friends are like super excited about SWOT. So it definitely has applications in the ice sphere. But I would check NSIDC. They're the National Snow and Ice Data Center, DAC. They have probably a ton of different NASA data products that deal with snow and ice regions too. I think ICESat-2 would be a great satellite to look at as well.
Awesome. Let me keep checking to see if there's more. Okay, so another question is, for the Pixel Cloud product, what is the approximate size of one pixel? Thank you in advance.
Oh no. I think it's, Mary, do you remember? Is it like, I know it's on the order of meters, but I don't remember. Is it 20 meters? Or is it two? No, it's smaller than that. Maybe what?
I just kind of heard something like 10 meters, but that the resolution kind of changes a little bit.
Yeah.
We can do some digging and follow up.
We can Google that.
Yeah.
It's in the handbook. That's gonna be my answer.
Yeah.
It's in the handbook.
Yeah. And while we're waiting for questions, let's see, actually there was another one I think that maybe we didn't, or that was kind of covered, but we can revisit it. Could you explain the uses of the different formats and when to use observation prior and assignment lake shape files? I think you kind of covered that in the description of it. So maybe not actually, but
yeah, I mean, it's a tricky thing.
yeah.
I can re-explain it real quick. So the prior lake one is defined by a set of prior lakes from a global database that Dita Wang led. So you should look into that. That can be found where I mentioned it in the PODAC cookbook. And the prior, so it's based on, it'll assign all the water pixels to those specific prior lakes. The observed is if it's whatever SWOT innately is observed, and if like different lakes that are in the prior database are combined in some way, like they've morphed together seasonally, etc., there will be no divide in the features. That's one of the main differences, but also the documentation in the handbook goes into a lot more finer details of what the differences are there. And then the unassigned lakes are just lakes that are not in the prior lake database, and they're just like, they could be lakes, they could not be lakes, they're just things that SWOT is flagging as water, etc.
Awesome, thank you. Let me double check to see if there's any others. None that are loading for me. I did want to point out, I just discovered this today, that there's also a binder application to search for SWOTs pass over time too, in addition to the KMC file. So that's another option if you're looking for the SWOT over pass times. as well.
Yes. I think in the chat they asked something.
Yeah. And
Is there a similar thing for Sword for Lakes? Yes. It's actually not just a Prior Lake database website though. It's on hydroweb.next. France hosts this awesome page that you can like look into SWOT data without downloading it first. But they have like a SWOT Prior Lake database filter. I think here, if you go to this website right here, hydroweb.next, and then the layer that you add, if you just Google on the top SWOT Prior Lake database, you can add that onto the map and just pan around there.
are there any lingering questions? If not, maybe we can take a quick break before the breakout sessions at the top of the hour, if that works. And thank you all so much for sticking around for this workshop. And thank you again to Cassie. This is, yeah, so cool to see it all in play and so seamless with the binder. So thank you again for hosting this for us. And we'll reconvene for breakout, yeah, at the top of the hour. Hope to see everyone there.
Sounds great. Thank you.
Hi, everyone. Welcome back. Maybe I'll briefly just go over the breakout rooms again, Michael, if that makes sense. Let's see. Okay. So for brainstorming, this is our session now, and we have an hour set aside, but we understand folks are spread out across different time zones and have different commitments. So there's no pressure to stay for the whole time, and feel free to come in and out as needed. So a traditional part of our meetings has been to openly discuss ideas for new joint projects. And we can also use this time for networking or follow-up questions for Cassie or ourselves. And let's see. So some questions that we can pose are, what did you find interesting about today's topic? Do you have more questions about today's topic, or do you have a research idea about SWOT? And so I think Michael has set up a couple of different breakout rooms that folks can choose to join. So one for socializing, one for questions, and one for brainstorming. And yeah, I think that was all I had for the slides, but you're welcome to, at this time, join a breakout room that you might be interested in. And let's see. So for the breakout rooms, yeah, I believe there's one for questions for the organizer, one for brainstorming, and one for socializing. And so if you'd like, you can join one of the three, and we'll kind of keep them open for however long makes sense. And yeah, hopefully now at this point you can, join a room and you should be able to unmute yourselves and discuss with others. And we'll be here and join the room shortly. Michael, is there anything else I'm missing about this part? Okay.
Yeah, or a way that we said it yesterday was this is the part the workshop is over for today.
Yes.
So no need to stay on. But if you'd like to chat with Cassie or discuss brainstorming ideas or socializing, that opportunity is available.
And Martin, if you have a question, joining that for Cassie, feel free to join the breakout group. But if you have a question about, how to join, feel free to post it in the chat or ask it also. And I may head into the questions with the workshop organizer. Okay. Oh, how can I join? Michael, are you able to?
Yeah. I can send you to that room, Martin. Yeah, if I can stay here a little bit. Oh, all right. Yep.
Sorry, Cassie, I didn't realize the breakout room's closed as I was talking, but let us know if there's any metrics that are helpful for you.
Oh, that would be great.
Yeah.
Yeah, if you could send just like the number of participants and like I have the questions, so that's good. But if whatever metrics you guys collect that you wouldn't mind sharing, I would love that for my team.
Yeah, definitely. And I think we can share, the recording too. And when we post it on the repository and all that, we'll be sure to share it in case it can go on the PODAC cookbook.
That'd be fun. I might have to put a recording through my clearance mechanism. So
Okay.
send me the recording and I'll put it through.
Okay, sounds good. We will do that. Anything else from any of the other organizers, or are we good to close this session?
Yeah, I think we are okay to close. Thank you again, Cassie. That was very awesome.
That was an awesome workshop.
Thanks. I had fun. I'm so glad.
Great. Thanks again, everyone.
Yeah, thanks.
Awesome.